Thank you very much for the introduction, and thanks to the organizers for putting together this conference. Yes, the talk is about unforgeable quantum encryption, and this is joint work with Gorian Alagic and Tommaso Gagliardoni. So this talk will be about generalizing security notions from symmetric key encryption to the quantum realm. And these security notions, they are really at the heart of the cryptography we use every day on the internet. So if you just open your browser, for example, to Baidu something, and if you then want to verify that actually your connection is encrypted, then you can click on this little lock symbol over here, and then there appears some information. If you click on this arrow, there's some more information, and then if you click on more information, you get actual information about the crypto that's used. And there's this line down here that gives you information, the exact crypto scheme that has been used, and there's this part in the back that tells you that it's actually an authenticated encryption scheme that is used. And what does an authenticated encryption mean? It just tells you that it has two properties: secrecy, so an adversary cannot learn what's inside the message, so in this case what website I'm looking at, and an adversary can also not intercept it and change it or forge it, so that I'm sure that it actually comes from Baidu. So also I'm kind of weirded out by the fact that Firefox tells you only about secrecy and not about authenticity in words down here. Anyway, so after this introduction, let's have a look what this authenticated encryption and related notions are, and how to generalize them to quantum encryption. To do this, let's start with a little family tree of security notions for classical symmetric key encryption. So as I said, there's like two main security goals. There's secrecy, and there is authenticity and integrity. So on the secrecy side, we have as the lowest level security notion for modern encryption schemes, indistinguishability of ciphertext under chosen plaintext attacks. So that means that an adversary that submits two plaintexts and gets one encryption back, which is chosen at random between the two, cannot tell which, even if he gets the help of an encryption oracle. Then we can strengthen this notion by allowing the adversary to play with the decryption oracle as well, but just before, only before submitting these challenge messages. Afterwards, he can only use the encryption oracle. We can strengthen it even more by relaxing this restriction and allowing the adversary to play with the decryption oracle also after receiving the challenge ciphertext. But it wouldn't be a lot of a challenge if the adversary was allowed to use this decryption oracle to decrypt the challenge, so we disallow that. Then on the authenticity and integrity side, we have integrity of ciphertexts. This is to encryption what is the EUFCMA for message authentication codes, and this EUFCMA is the notion that I talked about on Monday. And then we have the queen, or let's say the gold standard of symmetric key encryption, which is authenticated encryption. And it's just defined as integrity of ciphertext and indistinguishability of ciphertext under adaptive chosen ciphertext attacks. Okay, so now let's look at quantum. What has been done up until now? So the two notions down here, they have been generalized to the quantum case by Broadman and Jeffrey and Alagic et al. But the upper three notions have not prior to this work. And the question is, what's the difference? I mean, we just, step by step made them stronger and stronger. What prevents us from generalizing these upper notions here to quantum encryption? So to understand that, I would like to focus on one of the notions, and that's integrity of ciphertexts. And let me define it a bit more formally. So this is defined in terms of a game. Here we have an adversary, and he's allowed to play with an encryption oracle. So this is classical now, still. So he can send some messages to the encryption oracle, get some ciphertext back, and in the end, he's supposed to submit a ciphertext. And when do we say this adversary was successful? We say he's successful if this ciphertext is valid, because that's his goal. He wants to forge a ciphertext. But then also we have to require that this forgery is actually, it didn't come from the encryption oracle. So we have to require that the ciphertext is distinct from all the CI. Otherwise it would be trivial to fulfill, to achieve this forging. So what about quantum? Why is it difficult to make a quantum version of this? So to show you why it's difficult, let's just try it. So this is my first attempt to define quantum integrity of ciphertext. So what do we have to change? Of course, we need a quantum encryption scheme. So this has a classical key generation, but it has encryption and decryption algorithms that are quantum algorithms. And now the adversary can, of course, send quantum messages and get quantum encryptions. And he can submit a quantum proposed forgery. But now it gets tricky. So, of course, we can verify whether this decrypts properly, but how on earth can we check whether this is a fresh forgery? Whether it's not equal to one of the ciphertexts that the adversary got from the oracle. And this is, of course, it seems impossible because these they don't exist anymore, right? I mean, the adversary was playing and applied a unitary to a ciphertext possibly and submitted it again and so on. So they're gone for good. So that's basically due to no cloning. And on the other hand, if we suppose we had the two of them and would like to compare them, then this would be done by a measurement, and that would in general be a destructive process. This is also problematic because then we destroy the forgery of the adversary and then we say, okay, now it's not valid anymore, that's not very fair, and that would yield a weak notion. Note that indistinguishability under adaptive chosen ciphertext has a similar problem because here we have to enforce that the adversary cannot decrypt this challenge ciphertext. But this challenge ciphertext comes from a message that the adversary has submitted. So in the quantum case, we cannot make a copy of this either. So in that sense, it has exactly the same problem. Okay, so now I would like to present a solution attempt, and for ease of presentation, because the ciphertext case is more technical, I will use like a weaker notion, which is called plaintext unforgeability. So here we relax this, we strengthen this condition that the adversary is supposed to submit a forgery here, such that the decryption of it is different from all these query messages. And because encryption is in general a probabilistic process, this is a stronger condition and gives a weaker security notion. Now let's, of course, look at the quantum case, and let's be a bit more formal. So here, these cats were more of a cartoon, so let's switch to system labels. So these are now quantum systems. It's a message system. It could be entangled with the adversary's private space. He sends it, gets something back, and et cetera, et cetera. Okay. So again, the problem is that the registers MI and M star don't coexist. So here's some ideas how to solve this. One idea would be, instead of looking at the two messages, I can look at the channel that basically takes one of them as an input and outputs the other one. So although this involves like additional encryption queries and all kinds of stuff, it's still a valid quantum map. So I can look at this channel. And the idea would then be to kind of test whether this channel is the identity or not. Because if it's the identity, the adversary has been cheating, right? Then he has just used an encryption query to produce his forgery, quote unquote. We possibly have to do this using two games because to test whether the channel is the identity, we have to control, as the challenger, what to input into this channel. So we cannot allow the adversary to choose the input. But then on the other hand, if he wants to produce a forgery, he should decide on the input. So we resolve this by using two games instead of one. And this identity testing, it should be efficient, otherwise we cannot use reduction proofs in when later proving security. So how do we do this identity test? So one efficient solution and a simple solution is by Broadbent and Wainwright, where you prepare an entangled state, then you send one side of the entangled state through the channel here, and then you check, you just measure, is this still maximally entangled or not? And the output of this, or the probability that this will output an identity, is just basically equal to the inner product of the Choi-Jamilkovsky states of the identity, which is the maximally entangled state, and the Choi-Jamilkovsky state of this lambda channel. So there are other identity tests, but that don't need entanglement, but they are more difficult to analyze, and I will look at this. And we haven't worked out this possibility of other tests to test identity. So in the following, let's denote this identity test if the channel has input register R1 and output register R2 as id R1, R2. Okay, so now let's define the two games in terms of which we would like to define our notion of quantum unforgeability. So the first game is this game, and it's very boring because now it's just the same as this integrity game, except that we drop the first condition. So now the adversary is free to just make one query and output the result if he wants. He can also do something more complicated. But now we want to compare this game with a different game, which we call the QUF test game. So here, we just discard the adversary's input on every query, and then we initialize a new register, M1 prime, to encrypt. And I will tell you the input state for this register in a second. So now the adversary continues like he has been doing before, and in the end outputs a forgery. So now what we can do is we can use this identity test to test whether the channel from here to here is equal to the identity or not. And it turns out that if the message space is not too small, then we can actually do this in sequence for this one and so on up to Q. This is by a fact called the gentle measurement lemma. And now, in this QUF test game, we credit the adversary with success, quote unquote, if one of these identity tests here turned out identity. So if the adversary has cheated. So now we're ready to define quantum plaintext unforgeability. So we say a quantum encryption scheme is plaintext unforgeable if for all quantum polynomial time adversaries, the probabilities of winning the QUF forge game and the QUF test game are close, up to a negligible difference. And why is this reasonable? So let's look at the games again. So the idea is that to even win this game, to even get output anything that's valid, the adversary has to cheat. He has to query and then output whatever he got. And if he does this, then this game here will turn up cheat. So the idea is because we compare the two probabilities, we get something that actually certifies security. One thing that's kind of immediately clear from this definition is that it implies in CPA because we kind of hard-coded it into there. Because if the adversary could distinguish the two games, where one of them we supplied some fake ciphertext, then he could behave differently in the two and therefore break this definition. But that's not a problem because even in the information theoretic one-time setting, we know that authentication, quantum authentication, implies encryption. So we cannot expect to have a computational many-time notion of authentication to not imply encryption. And because the adversary has an encryption oracle, this should be this secrecy notion that is implied should be in CPA. So by this reasoning, it's kind of not a problem that we have hard-coded it in there. One important thing to check is that the classical restriction kind of behaves reasonably, and because it implies in CPA, we would expect that it is equivalent to authenticated encryption, and that's actually true. So if we now we define a reasonable classical restriction where we have to change the identity test a bit, we get authenticated encryption. It can be upgraded to quantum ciphertext authentication, and this upgrade also removes this requirement of a large message space. I can't, unfortunately, describe this in detail, but this is done via a lemma that says that every quantum encryption map has a certain structure where we first sample a classical sample, and then we attach it to our quantum input and apply a unitary. This lemma doesn't guarantee that this particular implementation is efficient, but at least from the definition side, this is fine. And in all the cases where we have used the definition for reduction proofs, we can also prove that this particular implementation is efficient. And then, basically, to complete this definition, we use the identity test idea on the quantum part, and we save a copy of the classical randomness to use like traditional comparison for the classical part. Okay, here's what I couldn't tell you in 17 minutes, and I see that they are actually over. We can make a definition of quantum indistinguishability under adaptive chosen ciphertext attacks with the same idea, because we can basically detect challenge decryption. And again, we do this by splitting the game into two cases, a detecting version and a free version somehow. Quantum authenticated encryption should be already done now, right? Because we could just define it by requiring both unforgeability and chosen ciphertext security, but there's actually a much nicer thing which we can do, because there's this real versus ideal characterization of authenticated encryption by Shrimpton, which is kind of made for this identity testing technique. So that way we get a much cleaner separate definition of quantum authenticated encryption. And this last point is actually extremely important, so I want to mention this. We can fulfill all these notions with a very simple scheme using a pseudo-random function that in fact only has to be post-quantum secure and unitary two designs. Okay, and then maybe this is my last slide here. This is a picture of the security notions. These are the notions that were proposed in the current work. This notion I didn't talk about. It's a one-time notion that provides ciphertext authentication, and we kind of wanted this because we wanted to have a strong lower bound that gives us the intuition that this is the right notion. So we show that this quantum authenticated encryption implies a computational one-time notion that is intuitively correct. Okay, so with this I want to finish and conclude by saying that generalizing authenticity and integrity notions to the quantum realm is complicated by the fact that we can't really compare things at different stages. And the approach that we solve this could be described as divide and conquer. We just divide the game into two, and therefore we can check one property in one game and the other one in the other. that way we can succeed in generalizing and get nice notions which can be fulfilled. Thank you very much.
Thanks. So we do have time for one question over there. Can you repeat the question, please?
Is there a reason why you don't use one more unforgeability? Because that would solve the issue that you have to compare.
Sorry, I acoustically didn't understand. What is it called? One more?
One more unforgeability. So the forger, after Q queries, is asked to output Q+1 ciphertexts.
So basically, as I kind of talked about in my talk on Monday, this is already for classical encryption against quantum. This is kind of not the right thing to do, because there can be attacks that need to destroy whatever I got from the oracle to produce a new forgery, and I want to protect against these. And in the fully quantum case, this is even more true somehow.
Okay, thanks.
So let's thank the speaker again.